Okay, I'm starting now then. Hello, my name is Ritam Saha. I'm second year student from ISERC Visva Bharati. Today's topic will be Lancaster law. It is for introduction. This Lancaster law models the dynamics of warfare. There's the battles, conflicts, anything. Um, so let's start. Okay. First, what are we gonna do today? Um, let's think what you're seeing in the screen. This is a battlefield. There are two sides, red and a blue. On the red side, we have our number of soldiers or units, and on the right side, here in the blue side, we have the number of units, and the units are variables uh, with which depends on time. So as it is a battle, the number will go down obviously, and what you can see here in A and B will uh, the n- num the as I have said, the number will go down as the time goes on. So how the number will go down? So the rate of loss is proportional to the force of enemy power, and this A and B, they are the proportionality constant. So with this, we are going to model our. This is this is how we are going to model it. Okay. So first is the generalized Lanchester law. What is where it is now? Yeah. The law. This is a set of differential equations. Uh, the differential equations are like as you can see, the dv dt equals to a r whole to the power p b whole to the power q, and dr dt equals to b in times b whole to the power p r whole to the power q. Now one thing here is this a and b, uh, they are called attrition parameters, and they are strictly negative numbers, as the rate is a negative. And as I have said before, R and B are the units of red side and blue side, and here P and Q are called P is for parameter for attacking force, and Q is the exponent parameter for defending force. Now, if we solve this differential set of differential equations, we will get this sort of results. Now, depending on the values of P and Q, there are three standard models. If P and Q both are equals to 1, we'll call that Lanchester's linear law. If P is 1 and Q is 0, we'll call that Lanchester's unique law. And if P is 0 and Q is 1, we'll call that Lanchester's logarithm law. The first two are mainly important in what is it in practical fields. The last one is not so important. So first we'll check Manchester's linear law. Now, what is this law look like? So as we have said, the P and Q both values are equal to 0, and if we put that there, we will see that this is what the equation will look like. And why it is why it is called linear? Well, it is called linear because this differential equation here, uh, as this is a battle, so at what condition it will be draw for the both sides. So when a r0 equals to b b0, this is the condition for which they will the battle will have a result of draw, and as the power is 1, so we'll call it linear. And solving this equation, we get this kind of solution. Now the assumptions we take for this linear law is are this: that that the firing with that I mean attacking. So a blue side will attack red side will attack blue side, but they will be evenly distributed. Targets must be visible. That means there cannot be any hiding, or uh, their targets must not come from outside source, somehow join inside in here. And after one target is eliminated, the units move on to next target. I mean, one red unit killed one blue unit, so then they will go to the next blue unit and attack it. There's one more thing that is important. As we can see here, the rate of loss is proportional to the enemy forces and also its own concentration. That is important. So this is what the dynamics actually look like of the battle if it is linear. Okay. So uh, what kind of battle we will call linear? Okay. So here is a simple diagram to explain it. Okay. So as we have seen here, uh, there are two sides, a red side and a blue side. They are both attacking each other, and they are both attacking each other evenly. So uh, when it will be linear, no, we will call it linear when one unit from red side can attack one blue unit at a time. It can it's not like multiple red unit can attack one blue unit at a time, or if one red unit can attack multiple blue unit at a time. It will be one red unit versus one blue unit at one time. So this kind of this kind of battle we will call uh, the linear. This kind of battle will follow the linear law. So for example, we can take let's say in the older days there there are sword in battles they use swords and lances and they fight each other. So one swordsman will only can fight only one swordsman in the opposite side. And in the modern day time, uh, you can say it is the battles between artilleries, where there is one artillery on the blue side and another artillery on the red side. Then the artillery will fire each other, but they can fire each other at a one time. Okay, so as you have said, linear law. So next we'll go to Lanchester square law. Now, uh, as we have said, the square law here, what it is, uh, we will see that we have what is it? Exponent parameters. Well, p is 1 and q is 0. So that is why we call it square law. And when this is the differential equations, and when we solve it we get this. And again, the condition for both sides to reach a draw is r square equals to b square. So as it is as we can see, this is the power r in square, so that is why we call it square law. Now what is the assumptions for square law? Assumptions, the only difference between the assumptions of linear law and square law is that the fire is directed. That means in the modern times we have guns. So one person with a gun can fire at multiple direction and multiple enemies at a single time, and also multiple enemies with guns can fire a single enemy at a time. That means the fire can be concentrated, and they uh, they fire at it. They aim at an enemy. Okay, and this is what the dynamics look like when it follows square law. Okay. So okay, so here we also have a red side in the here and a blue side in the opposite side. Now, as I have said before, uh, in here there is the linear loss constant that one enemy can fight one other enemy at a single time. So here what happens is multiple enemy can target one enemy, or one enemy can target multiple enemies as well. So as it is concentrated and directed attacks. Now uh, we go to logarithmic law. Mm, there is not much in the logarithmic law. Uh, it is when p equals to 0 and q equals to 1, uh, we get the logarithmic law. The equation look like this, and as you can see, by solving it, we will get the exponential solutions. And there is not practical applications in this much. Okay, so where are these uh, models are used? Um, According to Lanchester, he said that linear law are for the ancient battles, are hand-to-hand combat, or like there are battles going on, and two soldiers with sword are fighting each other, like one swordsman fighting another swordsman at a time, or as I have said, artillery fire or bombardments. uh, so in artillery fire there is like one artillery in blue side, one artillery on red side, and they are fighting each other until one artillery goes down. So when one artillery goes down, it will go to the next one, like this. And on square law, it is like aimed fire combat. When with any kind of modern fire, like in fire, the battles of World War II, the many battles we fought with uh, guns on the battlefield, and they were, if they are guns, that means they will be aimed. They will be directed at enemies, and if there is a small concentration of enemies at a point, the opposition side will take guns and fire at them. So now the next thing is mixed forces. Now, as we have seen, there is a two side, a blue side and a red side. Now, in real combat,
May I ask a question?
yes, sure.
Uh, so you are not mentioning any results here yet. You're just mentioning the way the model are built out and like which part of model, which model are for which part of the battle or like which type of the battle. So are there any results involved or any simulation?
Can you repeat your question?
Uh, Are you showing any results for these models, like simulations or whatever thing?
No, I am not showing any actual results.
Okay, okay,
There,
just move on.
there are actual results, but uh, this the models I have shown, um, the square law or the linear law. Uh, there are people who have tried to fit this kind of model in world in real world battles, but what we have seen is that this square law or linear law are not really that it does not fit in any real life uh, combat. There was a battle of there was in Second World War. There was a battle between Germany and Russia. That particular fight, that particular battle was well recorded, and it was modeled later on. But when we tried to fit it, what we found was um, the parameters A, B, P, and Q. The P and Q, this value, uh, they does not match any of these three standard models that I have shown. So as I have, so the
So,
three models, uh, they are, you can say, uh, practically there are no battles recorded that can be accurately modeled by this three models.
they are the model to start with, and they have purely solvable analytic solutions, right?
Yeah.
Okay, okay, thanks. Please move on.
Okay. So there are mixed forces. So as I was saying, so we have a blue side and a red side. So now what now blue side and red side, so each side does not necessarily have one single type of force. There can be multiple type of forces. um, so let's say the red side have two type of forces, R1, each type of forces has R1 soldiers and R2 soldiers. Similarly, in blue side, they have B1 soldiers and B2 soldiers, and they have combat effectiveness B1, B2, and A1, A2. So now, in this kind of problem, how we will deal with it? So in square model, we have seen that the in this sort of problem will give rise to this kind of equation, where the parameters will simply be the average of them, the weighted average, you can say. Um, as for example, you can say in a battlefield, there are a unit uh, which carries assault rifle and another unit which carries submachine gun. So assault rifle and submachine gun, they have different battle powers. So they will yield different results. So with these, the the battle, the parameters, and the number of troops, we can calculate the average parameter, the average value of the parameter, and we can use it to get a more simplified solution. So now another, here is the question: which one is a better solution? So I think I have already said that there none of the models I have shown actually is a very good result in actual combat data. So, but still, if we check the properties of these models, so we can see that when these forces are directed, the square is better than linear law, and when there is they're evenly matched and one-on-one fight, uh, the linear one is better fit. Um, but in our modern day, when we are trying to model it, there are various ways we can um, make a better fit. One would be the Lanchester generalized law, which I have shown in the start. So, if we use this one, uh, we have seen a pretty good fit for many of the battles from World War II. And another way to get uh, good results, good model fittings is that uh, by combining the linear law and the square law. This is because um, people studied how uh, the battles occur, and they have seen that many of the cases, uh, one side usually uh, uh, gets direct. So there is many cases where we have, let's say, a blue side and a red side. Now the situation comes like this, where our red soldiers are directing their attacks on blue soldiers, but the fire from blue soldiers are not directed. So, in these kind of cases, linear and square law, the combining them will get a better fit. Um, One kind of example from combining this linear and square law, uh, this is a similar problem you can get. Uh, you the competition between species model, if we study that, you can see um, that in that kind of model we are using the linear law and the uh, square law at the same combining them and making a model. So other than that, there's we can add other parameters like the force, the two side, which one is on defensive position, which one is on offensive position, or another way, another parameter we can add is uh, how much terrain is giving advantage to one side or another side. This kind of modifications kind of improve the models. So, and this is here I end my presentation. So, any questions from anyone?
I have a question. On slide 16, how do we, justify the parameters on, yeah, combat effectiveness? How do we know how much combat effectiveness we should, quantify for a certain army, let's say, or a force?
how much combat effect? So you okay? That is as I have said.
How do we determine?
How do we determine? Okay. Look, first, we have to consider what is combat effectiveness is. For now, if we look at it for different P and Q pairs of values, the physical interpretation for combat effectiveness is different. So first, let's look at the square law. Square law, combat effectiveness is like how much uh, uh, okay, we have, sir, let's say a blue side and a red side. Now one how much damage one red side causes on blue side. This is the combat effectiveness for square law. And if we take a look at linear law, um, in linear law, you will see that the loss is proportional to the enemy power and as well as its own concentration. So if we try to define the combat effectiveness here, it will be like how much damage uh, one opposing soldier, one opposing unit causes on another unit. Do you understand what I'm trying to say?
Yes. Okay.
Okay. So,
But I mean,
I would like to. Okay, go on.
okay, you are saying something. Say, hello.
Hello. Yeah, I'm Krishna.
hello. Oh, sorry.
I have yeah. This I
Uh,
want to comment on the question you answered. So
Yes.
while modeling, we have some free parameters. Okay. So those free parameters are determined from the data sheet of the situation we are modeling. So basically, to determine B1, B2, A1, A2, or any other parameters, we just fit them with the data and determine them from the data sheet we have. So that is one way, like how I do my simulations. That is one way of determining the parameters in the equation. There can be others also. I just, yeah.
okay.
I was here for a very brief time. My internet was lagging a lot. But what you're describing is essentially a competition model between species, right?
Yes, you can say that it is essentially competition between two species.
Are you assuming, so let's say there are two armies. So are you assuming that one of the army's defensive capabilities, or are you considering only offensive capabilities? And I didn't
Uh,
see the equations. I just got a glimpse of them very briefly. I couldn't
no,
properly see the equations. So
it is only the offensive capabilities of both sides.
okay.
We
So
can add
what other kinds
defensive.
of systems? Okay, right. What other kind of systems can you model using the same kinds of equations?
What other kind of usually what I have seen is that other than this battles or the species competition, um, I have not. Uh, I don't think there are any I could think of.
Okay. You defined something as the attrition parameter. So I just saw for very briefly. Could you explain that? I
Okay.
missed that part. I accept I missed that part. My
Okay. So here, here you can see in this differential equations, we have this A and B. We are calling it attrition parameters. So if you look at the differential equation, you will see that the loss of one side, the rate of loss of one side is proportional to the battle force, right? This
Mhm.
attrition parameter is the proportionality constant of that. Um, now,
Physical, what does it mean?
okay,
What's the
physical.
physical interpretation of that?
Okay, physical interpretation. You can say it like this. Like we have the blue side and we have this red side. So one unit from red side, how much damage does one unit from red side causes another unit from this blue side?
How much? Okay. So,
So this is one way we can define it.
okay. Imagine P Q equal to 1. Okay. Right?
Uh, can
Imagine
say
P
that
equal
again?
to Q equal to 1.
Okay, okay,
Imagine P equals Q equals 1. Okay.
okay.
Can you think of a can you think of a exact physical interpretation of the attrition parameter in terms of, let's say, number of units killed?
Okay, can you say that again one more time?
So suppose P equals Q equals 1, right?
Yes.
Suppose P equals Q equals 1, then the equations are dBdt equals A RT BT and dRdt equals B BT RT, right?
Yes.
So can you think of a physical interpretation in terms of A and B with respect to, let's say, the number of units killed or something like that?
Yeah, it will be like the same thing. We have one unit from Red Army, and we have another unit from Blue Army. So, how much damage this Red Army causes the Blue Army, or vice versa? This is how we get the value of A or B.
Okay, fine. Right. Hello? Yeah, fine,
Yeah.
fine. Cool. Yeah, I think I lost connection once more. So you are just interpreting it as some kind of a proportionality constant over here. Just how much
Yes.
damage is done in that, right?
Yes. You can also say it like that. Like if one uh, so let's say it is the value is uh, 2. uh, uh, okay,
Hmm.
let's take a simpler one, this square model. So let's take the value of a is 2. Okay. So this so what this a means here is at a single time, the one red unit can kill two or can eliminate two B units.
Yes. So basically, your attrition parameter means that how many. So, for example, how many blue units are eliminated by a single red unit,
Yes. So
isn't it?
yeah.
That's basically the physical interpretation.
So there is when we say how many, there is one small problem with that. It is let's say A is 1.2. So we cannot eliminate 1 and 2/10. So that is why I am saying
No,
damage.
of course.
So
There- these are scaled with certain. Of course, I think these are scaled with certain overall populations. mostly saying in terms of predator-prey systems, but even in this case, I think they're scaled to a certain population. So these are not, one or two are not exact numbers. These are certain scaling is done over here.
Yeah,
You get my point?
that is why I will say unit basically. So
Right,
that does
right,
not
of
mean
course, of course.
unit.
Right, right. Of course, of course. It is obviously scaled with certain things. So basically, it's like in a certain sense, it's per capita damage.
Yes.
That's the kind of, right, of course.
Okay. Any more questions?
What is there any? I mean, apart from developing video games, is there any practical implication right now? I mean, in today's present world, because I mean, there are
Um,
wars, but not that much as well.
yeah, and I hope there is not much. And anyway, what these models are actually doing is that one, they are used for analyzing past battles. Uh, Second, these kind of models are used in some species competition, species competitions. Like let's say we have two types of ants, and how are one ants are some more successful than others. So we're trying to model. So these kind of models are used to model that kind of scenario. um and as you said, video games, so they're not basically that practical, but yeah, we use them in video games also. Other than that, I have not come across any uh, other kind of scenarios for now. Don't I don't know if there are other any applications.
In a way, can they be used to like maintain peace as well?
um that is I I really don't know the answer to that question, because they are
I would just answer. Yeah, go ahead, go ahead.
okay. What I'm trying to say is this model uh, this model models the dynamics of war, like how the war goes on from start to end. So this does not like model any battle tactics or any kind of thing. So other than the dynamics, it does not do much for a battle.
So, okay,
I'd
thank you.
just like to answer on his question. I'd just like to add to his question a couple of things. So you are talking about the relevance in the current scenario. Models of sexism are based on the Lanchester's model. If you just look up for models of sexism, so one of the models has exactly similar kinds of equations, and the model is used to basically derive that women are at the blunt of sexism a lot more than men. So it's based on the similar model. And other than that, these are very classical competition systems that are used a lot in predator-prey modeling. And those leads to very interesting dynamics. If you were to look at the dynamic side of things, they lead to very interesting chaotic dynamics if you wish to study on it.
Okay, thank you.
Do we not need more variables for chaotic dynamics?
Yeah, we need three. You at least you can't get chaotic dynamics with two systems,
Yeah,
with two
that is like,
equations.
can we use it to model for between two human groups competing over some resources? Are there some real world examples for that?
Yes,
Anyone, Archie and Ritam?
there are not any example exactly for humans, but there are few models that there is, I think, I have seen one where they are trying to use this for a certain species. Okay, there is a this kind of model where there is one small area and there is two species of birds living. So they're trying to model how this species dynamics goes on as there's a limited resources on that small area, like let's say on a small island. So there is a two bird species and how their species dynamics goes. Here in that kind of cases, this Lanchester's model are used. So if bird species can be used, so then human species they can also be used for if you take simple assumptions on that.
Have
Does
you
that answer?
tried modeling this system on a computer yourself? Have you numerically modeled this system on the computer yourself?
I have not tried myself. I have actually read a few, but they actually tried, and I tried to copy it myself. But I did not get. I actually what tried is I there are data I got from few papers, and I tried to use the square law, but it is nowhere near close a fit. So I kind of discarded the
Okay.
whole thing.
It's
I
fine.
think
It's fine. I'm just asking.
all the
Yeah, go
models
ahead.
that uh, he has shown here, there is analytic results are possible for all of them, I think, right?
Analytic
So there is
results,
nothing to.
yeah, they're possible.
So I mean, like there are closed form solutions we can write for almost all models, right?
Yes.
So so I don't think any simulation is required for that, right? Archie?
No, I don't think you explicitly need simulations for that. But if you do simulations, you'd get a feel of how things work out for yourself. And the reason I said mention simulations was this: if you go into three systems from here, so there are so imagine there's three groups of people fighting against each other. A fights B, B fights C, C fights A, this kind of a system. So you can try and model those things to see if you get any chaotic behavior. Because if you get chaotic behavior, you won't find closed form solutions for them. You can try out, look on the net and find if there are three system modeling for Lanchester's laws.
I think there must be something more in the domain of competition.
Yeah, there are competition models between species. I'm pretty sure there are competition models between species, and there are lots of them. But since he's trying out Lanchester's law, that's why I mentioned that you can find out similar kinds of systems for three variables and you sit down and do the simulation yourself. You'll find a lot of interesting dynamics coming up.
Okay, hello. One thing I want to ask that Tishman Bhaiya was told that there is maybe three possibilities. That means that three participant can be there with this thing. I can get that.
Okay, let's say
Yeah, there can be, when you have three participants, you can have a lot of possibilities.
No, if there maybe there are multiple participants also, more than two, they are fighting to each other, same resources, like a multiple species are fighting to each
Yeah,
other. That can be possible.
we
yeah,
can model up to
that can
any.
be possible. So I'll just give Shushima a very good example, a very simple example. Imagine there's a tropical food chain, okay? So there are different kinds of herbivores, right? And none of them eat each other, but all of them are competing against each other for the resources.
Okay. Okay.
Yeah, that's an example of competition between three. So you can imagine three species, and you can imagine the competition between them.
Okay. Okay. I get it.
Yeah.
Like a squirrel, monkey, and human competing for a guava on guava tree.
Yeah, yeah, yeah. Of course, a squirrel, a vegetarian, and an elephant can compete against each other.
With this respect, I had one more question. Are there any like corner cases or cases in which this holds less accurate than other cases?
Okay. First of
Hello?
all, I hello. You can hear me, right?
Yeah, yeah. Yeah, no, it's
Um,
fine.
okay. As I have seen the linear law or Lancaster law, they are okay. So as I in the title it says that we're trying to model warfare. So from actual warfare data, what I have seen is that uh, they are not uh, they do not give any kind of meaningful result that that can actually we can say this is modeling the warfare. So why that so uh, why they we are so interested in them is solely because they're pretty simple, you can say. So, as I have said, in particular Germany versus Russia battle, um, I have used the square law, but they are not a good fit at all. You get that?
Yes. Okay.